Hey, it's Mr. Lanham. Let me go over a few of the answers for the homework tonight. Chapter 10 practice problems, questions 1 through 8. Won't go over all of them, just a few. Okay, question number 2 had an answer of work is equal to 28,875 newtons. So let's see how we get this answer. So this is the one where the kids push a car with a force of 825 newtons for a total distance of 35 meters. Then the problem asks how much work was done on the car. So that's our unknown variable. Remember, if you set it up this way, the fact that you've got force, distance, and work all lined up, this capital W is work, got all those lined up, that helps you with your equation nice and easy. Because our equation needs force, distance, and work. So that's really easy. It's work equals force times distance. So now all we have is the math of solving, which is simply plugging it in. Work is our force. We pushed 825 newtons on the car, a total distance of 35 meters. Check your units. We have newtons times meters, and a newton times a meter is a joule, so we have set it up properly. And we end up with an answer of, let me look it up again, 28,875 joules. And that is our answer for number 2. Okay, for 3A, we have a climber with a backpack with a mass of 7.5 kilograms. Takes them a time of 30 minutes to hike up, and the distance they go is 8.2 meters. So there's our given information. What they're asking us to do is find how much work, how much energy is transferred to that backpack. Now the equation for work is force times distance. You'll see that we've got distance, but we don't have force. But if we'll remember from Newton's second law, force is mass times acceleration. And the acceleration in this case is acceleration due to gravity, because we're talking about a vertical climb. We're going up. The force needed to lift it is the mass times the acceleration due to gravity, which you'll recognize as the weight of an object. Now that is a lowercase w for weight, whereas this up here is an uppercase W for work. The neater your handwriting, the better off you'll be at that. Mine's mediocre. Now hopefully at some point, could have been earlier, maybe later, you'll realize that the time is just extra information. It's not something that you need in this problem. So to set up our equation, work is force, and the force is the weight of the object, mg, times that distance. So g is a given from a long time ago. G is 9.8 meters per second squared. So all we have to do is plug it in. We have a mass of 7.5 kilograms times 9.8 meters per second squared, that's g, times a vertical distance of 8.2 meters. Now before you get calculator happy, you get kilograms times meters per second squared, and if you recall, that is a newton, and a newton times a meter is a joule. So we do have everything set up properly. So our work is all these numbers added together, which comes out to be 602.7 joules. Now keep in mind that is the energy given to the backpack. And part B is actually asking something slightly different. In this case, they're nice enough to give you the weight of the backpacker at 645 newtons. To calculate work, you take the force times the distance, and in this case the force is the weight. So if you don't mind, I'm going to write it this way. However, don't be tempted to stop here because the problem says the weight of the person plus the backpack. So this is the person, and then you also have to figure out the weight of the backpack, which is right here. So this is figuring out the weight of the backpack. So it's the mass of the backpack, 7.5 times 9.8 meters per second squared, and the total weight of both is what we need to use in that equation. So when we work it all out, the total weight comes out to, let's see, I wrote it down over here. Okay, it's 718.5 newtons. Again, that's the total weight of the person and the backpack. To find the backpack, it was the 7.5 times 9.8, gives you a number. I wrote it down somewhere else. Our distance up was the original, what was it, 8.2? Yeah, 8.2 meters. And a newton times a meter is a joule. So when you multiply all this out, you get an answer of 5,891.7 joules. So that is the energy exerted on the backpack and the person. So as expected, it is higher than the work done on the backpack. Okay, the next problem, I think it's problem 4. I've got the numbers, but I don't have the book in front of me. Is a different type of problem, and this is one where we are doing some work in the horizontal direction, but to do that work, we're not pulling in the direction of that work. We're pulling with a force at some angle theta. The problem is, work is done by a force across the distance, and that force is only the force in the direction of the work. So, as you're probably guessing, with the vectors here, if you think of an x and a y axis, let me show you what I mean. What we end up with is we have an x component of that force. So the x component of this total force right here, you can think of this as your resultant, and this is the x component of the resultant. So the x component of this force is in the direction of the work. That is the force responsible for doing this work. So what we're going to do is we're going to use our generic equation for work, which is, and I'll call it the force acting, well, the force times the distance. And the catch is this force has to be in the same direction as that work. So the way that I've written this, just plain F is not the same F as up here, because that must be in the same direction as the work. So it'd be a lot better if I go ahead and write f of x, because that is the component of force acting in that direction. If you remember that the x component of a vector is equal to that vector, or the r, that vector, times the cosine of theta. So the work is equal to the vector itself, force, now that is this up here, times cosine theta, and this business inside the parentheses is the x component. So remember, to find the x component, you take the vector times the cosine of theta. Let's say the exact same thing. To find the x component, you take the vector, multiply it by cosine theta. So our equation is that force times the distance. So let's go ahead and include the distance. So it looks complicated, but you're essentially just taking that force, multiplying it by cosine theta, and that gives you f of x. which is the force in the direction of the work. So this is the basics of how you do these problems. So in the problem, which I cannot remember the number, we have, I believe, 255 newtons pulled at an angle of 50 degrees. So if you want to picture, you get a box and a rope attached or a wagon with a handle, you don't always pull perpendicular to the ground unless you're really short or it's really tall or you're bending over. You pull at an angle. It's just kind of more natural and easy to do. So what you got to remember is that the work is in this direction and the force that you're actually that's doing that work is only a tiny component of that upwards force. Now here's something to illustrate that. What if I pulled straight up? If I pull straight up and down, there's no x component. So I will not do any work side to side. Any work I do is going to be in the up and down direction if I do any. So to find this particular problem, what we're going to do is we're going to use the same equation. I've kind of listed my givens up top. Is the force in the direction of the work. Force is always in the direction of the work, times the distance also in the direction of the work. And I've got to make sure that I really understand that that's what I'm talking about. So, I mean, that's the total force, if you will. No, that's really not a good way of saying it. That's the, like I said, that's the force in that direction. So the force in that direction is the x component. To find the x component, we're going to do f cosine theta times the distance. And now we're going to solve by plugging it in. Work is the overall force, 255 newtons, times the cosine of 50 degrees. I know my S looks a lot like a 5 there. Does that help? And the distance was, let me go find that, 30 meters. So we had pushed it along for a direction, or for a distance of 30 meters in that direction. So when you multiply all this out in your calculator, you get an answer of, well, the answer that the calculator gives doesn't matter if it's wrong. Always check your units. Newtons, there are no units here, times meters is a joule, so it must be right as long as I plug everything in right. And I get an answer of 4,917, and the unit for work, that is joules. So that's the basics, the basis of it. The key is, when you're working this problem out, this equation is all in one dimension. That force must be in the direction of that work. The distance in the direction of the work. Again, if I pull 90 degrees up, down, I won't do any work side to side. It's got to be parallel to that. Maybe that was a better way. No, that's perpendicular, not parallel. Never mind. Okay, so hopefully this was enough to get you started at doing some of these other problems. I'm going to leave it there. And I'll have the book up in the front of the room so you can check the answers as needed.